Hi students, we've spent the last couple of weeks looking at polynomial functions and rational functions. Now we're going to switch gears and look at a class of functions called exponential functions. This unit is going to center on exponential functions and then eventually logarithmic functions. For now, let's start with an example of an exponential function. Let's consider the function f of x equals 2 to the x power. Now, this looks similar to a polynomial function, g of x equals x squared. I'm going to write versus g of x equals x squared because I want to compare and contrast these. So this is an exponential function, f of x equals 2 to the x. And it does look similar in a way to a polynomial function we've seen before, x squared. Both of them have 2's, both of them have x's, both of them have exponents. But the big difference here is that with an exponential function, the exponent is inside the exponent instead of the base. When we have a polynomial function, the exponent is always a whole number, whereas with an exponential function, the exponent is actually going to be a variable or contain a variable. So what I want to do is I want to make some quick tables of values so that we can compare these two functions, and then we'll take a look at the graphs. So first, we'll make a table of values for our exponential function f. So let's pick some numbers. Let's take a look at -3, -2, -1, 0, 1, 2, and 3. Now at this point, I don't think we've looked at a negative exponent yet, so we're going to take a glance in a moment, but let's start with 1, 2, and 3. So if we look at this function when x is 1, 2 to the first power is just 2. When x is 2, 2 squared is 4. And when x is 3, 2 to the third power is 8. 2 times 2 times 2 gives us 8. Now, we're going to have a couple of very quick rules that help us deal with 0 as an exponent and with negative numbers as an exponent. So, if we look at 0 as an exponent, if we have any number raised to the 0 power, that is automatically going to be 1, except 0 to the 0 power is undefined. So in this case right here, 2 to the 0 power is going to end up being 1. One way that we can see how this works is every time we decrease the power by 1, we're dividing by 2 because we're losing a factor of 2. 8 divided by 2 is 4, 4 divided by 2 is 2, and 2 divided by 2 is 1. So this kind of fits the pattern. And then when we have a negative exponent, this is going to end up giving us fractional values. If we continue to divide by 2, 1 divided by 2 is 1/2. 1/2 divided by 2 is 1/4. 1/4 divided by 2 is 1/8. And so the rule that we have here is if we have a number raised to a negative power, we can actually turn it into a fraction, and we can put that same quantity in the denominator, but with a positive exponent. So if we wanted to look at 2 to the -3, for example, 2 to the -3, we could write this as 1 over 2 cubed, and we already saw 2 cubed was 8, so we get 1/8, which matches what we have here. So this is our table of values for 2 to the x power. Let's take a moment and plot these points and see what we've got. So we've got the point 0, 1, 1, 2, 2, 4, and 3, 8. And then if we look to the left, we've got -1, 1/2. We've got -2, 1/4. We've got -3, 1/8. And so we can see that these points look like they're on a smooth curve. And in fact, they are on a smooth curve. We can connect these dots with a smooth curve like this. And then to the left, we are actually asymptotically approaching the x-axis. Because when x gets larger in the negative direction, it becomes a smaller fraction when we look at the function, closer and closer to 0. So this is our f of x equals 2 to the x. It almost looks on the right-hand side like a parabola. It looks very similar to x squared in a sense. However, it is definitely not. The shape ends up being quite different. And what I want to do is I want to show you a graph from Desmos to compare these two graphs. Here is a screenshot of a graph from Desmos, and this includes f of x equals 2 to the x power, as well as g of x equals x squared. Now here we can actually compare the two and see that they're very different. While we know both of them are increasing as we move to the right of the y-axis, and we can see that here, you can actually see that the exponential function eventually overtakes the polynomial function, and it grows much more quickly than x squared. In fact, even if we were to compare this with x cubed, or x to the 4th, or x to the 10th power, there is a point at which the exponential function greatly overtakes the polynomial function and grows much more quickly. In fact, you've heard of things, I'm sure, that grow exponentially. The reason we have this term, and it means something grows so quickly, is because when we have an exponential function, it ends up getting very large, very fast after a certain point. Of course, in the beginning, the function is growing very slowly, but eventually it starts to grow more and more quickly, and it shoots up like crazy. So this is one of the differences between a polynomial function and an exponential function. And I just want to explore this a little bit more. I'm going to expand our table of values here. I want to include 10, 20, and 30 in our table of values. This isn't actually in our graph. Our template doesn't go far enough, so this isn't in our graph. But if we were to evaluate 2 to the x for x equals 10, 20, and 30, well, 2 to the 10th power is 1024. So that grows very quickly. 2 to the 20th power is 1,048,576. And 2 to the 30th power is 1,073,741,824. In comparison, if we looked at our other function, x squared, and we evaluated it here, if we look at 30 squared, that is only 900. So if we compare these two functions when x goes all the way out to 30, f of x is already over 1 billion, and g of x is just 900. So exponential functions grow very quickly compared to polynomial functions. In the next video, we'll look at more examples of exponential functions and their graphs so that we can get a little bit more comfortable with them.